Hello everyone, welcome back to my channel. In this video, I would like to demonstrate quantum teleportation on IBM Quantum Computer. So in the previous videos, I have shown you how to prepare a Bell state using Hadamard gate and CNOT gate on IBM Q. And the interesting thing about the Bell state is that the entangled two qubits can be very far away from each other. And before the measurement of each qubit, you have no idea whether it is 0 or 1. But if you measure the left qubit and it turns out to be 0, you know remotely that the right qubit must be in the state of 0. And if you measure the left qubit and it shows 1, then it remotely decides what is the state in the right qubit, and that it must be 1. So this seems to be some interaction that is faster than speed of light. However, this is not against the relativity because no information is transferred. Yeah? But on the other hand, this entangled state, for example, we can make it into entangled photons, and we can separate the entangled photons using optical fiber. And it seems to be a nice way to transfer information. But how can we transfer information using Bell state? If you reformulate the problem that Alice wants to send an arbitrary quantum state to Bob, and this quantum state is encoded in one qubit that Alice has in her quantum computer, and this quantum computer can be very large. It has to be in the dilution fridge, so it is not very possible to ship this qubit physically to Bob using express delivery. And even if Alice can do that, this process could be also too long and too slow. So is there a faster way of transferring this arbitrary quantum state to Bob? And it turns out that we need two channels, one quantum channel and one classical channel. So this classical channel is something that we used every day. It's, for example, internet or phone or something else. Yeah, and quantum channel can be optical fiber. Yeah, because optical fiber can transmit entangled photons, and photons can carry the quantum state. So the first step is to prepare a Bell state. Prepare a Bell state entangled two photons, and Alice keep one photon and send another photon through the optical fiber to Bob. And now she entangle her part of the entangled photons to the qubit that contains the quantum information. And then she measures the photon, and the measurement outcome would be either 0 or 1, and we say that is M2, and M2 is the result, which is 0 or 1. Then she apply Hadamard gate on the qubit that she has to basically destroy indistinguishability or shuffle the qubit, and then measure the qubit. The measurement result is M1, which is again either 0 or 1. And upon measurement, the information in the qubit that Alice has is destroyed. And this is necessary because we know that we cannot copy quantum information. Yeah, so we cannot copy quantum information to two copies, and that is not possible. So in order to transfer this quantum information to Bob, Alice has to destroy her copy of the quantum information. Okay, and then the essential part of this process is that the result of the two measurements has to be transferred through the classical channel to Bob. And this result is used to correct the quantum state of the photon on Bob's side. Yeah, so Bob now receives M2 and M1, and what he does is that if M2 is 1, then he first apply an X gate on the photon. And X gate means that you change 0 and 1. You flip 0 and 1. If M2 is 0, he does nothing. Then, if M1 is 1, then he applies a Z gate on the qubit. If M1 is 0, he doesn't do anything. It can be proved that the resulting photon is in the same quantum state that Alice wants to transfer. Yeah. And of course, you may say that, okay, now the quantum state is encoded in the photon. How can Bob transfer that into his physical qubit in the quantum computer? And this is easy because we can use a swap operation that I mentioned last time. Okay, so to summarize this using a quantum circuit diagram that is shown on the right upper side, that the uppermost qubit is actually contains the information that Alice wants to send, and this beta 00 is the Bell state photon, and one photon gives to Alice and one photon gives to Bob. And Alice does the entanglement of her qubit to the photon using a CNOT gate, and apply Hartmann gate, do one measurement, and use the result of the measurement to control the Z gate. So these two vertical lines are basically the classical control gate. Yeah, and classical control gate means that you first do the measurement and then use the outcome of the measurement to control the quantum gate here. And the difference between classical controlled gate and quantum control gate that we used before is that quantum control gate doesn't involve measurement, and you know that after the measurement the quantum state collapses into a deterministic state, and the quantum information is erased. Okay, so there are more equivalent quantum circuits that does the same job of quantum teleportation according to the principles of quantum circuits that I show on the next slide. The first principle is deferred measurement, which means that the measurements can always be moved to the end of the circuit, and classical controlled operations can be replaced by quantum controlled operations if the measurements results are used somewhere. And then the principle of implicit measurement is that qubits not measured at the end may be assumed to be measured. So this principle is generally correct, but there could also be some counterexamples. So, yeah. And according to these two principles, you can write some more equivalent circuits. You change the classical controlled gate to a quantum controlled gate and move the measurement to different places. So those are different equivalent circuits, and here this basically writes out how you generate a Bell state, and this is another version of the quantum teleportation circuit. Yeah, and here on the right down corner we have the original quantum circuit, and on the left down corner we change the classical controlled gate to a quantum controlled gate. Yeah, and you see that this classical controlled X gate corresponds to the quantum controlled X gate, or is the quantum controlled NOT gate or C NOT gate, and this classical control Z gate changes to a quantum control Z gate, and then the measurement moves to the end. Yeah. This Hartmann gate here is not necessary, so we will just delete it. And on the IBM Q computer, we will use this circuit to show the quantum teleportation. And I will show hands-on in a minute how to construct the quantum teleportation circuit on IBM Q Quantum Computer. And this is the circuit. Yeah, so we prepare some arbitrary quantum state on Q0 qubit, and then try to move it to Q2 qubit, and we measure on Q2 qubit to see whether we have succeeded in transferring the information from Q0 to Q2. We want to test phi equals 0 or 1 or some linear combination of 0 and 1. But the question would be that how can we prepare the Q0 qubit into these different states? Zero state is easy because it is already initialized to 0, and if we measure the 0 state, it is 100% 0. If you want to change it to 1, we need to apply an X gate on the 0 state, which changes from 0 to 1, and the measurement will turn out to be 100% 1. To prepare 0 plus 1 over square root 2, I have shown you before that you need a Hadamard gate to change 0 to the superposition of 0 and 1, and the measurement would turn out to be 50% 0 and 50% 1. And then, if you want to have a different combination of 0 and 1, you may want to consider this rotation gates. Ry is the rotation against a y-axis, and you can specify the angle that you want to rotate, after which you will get a continuous spectrum from 0 to 1 state. And in this case, we use theta to be 120 degrees, and then resulting vector would be 0 plus square root 3, 1 over 2. And the measurement is 25% 0 and 75% 1. And the reason is that 0 is 1 over 2 square, that is the probability, and the square root 3 over 2 square, that is 75% probability of state being in 1. Okay, so that's all for the theoretical part, and I will show you hands-on how this works in the IBM Quantum Computer. Thank you for watching. I hope you learned something. If you like my video, I appreciate your like or subscribe to my channel, and I hope to see you next time.